Okay, in this video we're going to look at the properties of alkanes. In order to do that, we need to get into kind of things at the chemical level. We need to look at some of the forces or some of those things that are going on at that chemical level. So to start off with, there are two types of forces or bonds that we often refer to in chemistry. One's the intramolecular and the other one's the intermolecular. And I'm going to focus on the intermolecular, but let's quickly, just to quickly go over the intramolecular. The intramolecular is basically what we've been looking at so far. If we've got a molecule, say like ethane, the intramolecular bonds are the ones holding the atoms together inside each molecule. So those are those lines, the covalent bonds that we've been drawing, where each atom is sharing electrons with another atom. So an intramolecular bond is basically a covalent bond. And really, so this is an intramolecular bond. And we've got a pair of electrons here, and it's the force of attraction of the nucleus of the carbon atom, which is positive, being attracted towards those negative pair of electrons in here. And the positive nucleus of the hydrogen atom also being attracted to those electrons. And that force of attraction is what's holding this entire molecule, this group of atoms, together. So an intramolecular force are the bonds inside the molecule holding the atoms together. An intermolecular force is the force of attraction between molecules. So if I have another ethane molecule, so I'll just draw that one in. Sorry for my bad drawing. So if I have another ethane molecule, the intermolecular force, or the intermolecular bond, so same thing, it's a force of attraction between two things. Bonds are a force of attraction between two things. So the intramolecular were these bonds holding the molecule together. The intermolecular is the force of attraction between two molecules. So there's a force of attraction here, and it's kind of, don't know really whether to draw it as lines or how to draw it, but there's a force of attraction between this molecule and this molecule here. Grab another colour. So there's a force of attraction in between these two molecules, which holds the molecules together. That's the intermolecular force, and this is what keeps the molecules inside a liquid stuck together, or in a solid stuck in place so that the material is actually solid. And we'll look at that in a sec. So intermolecular is the force between molecules, and intra is the bonds within the molecule inside it. So we're going to focus a little bit on the intermolecular, because that tells us, explains a little bit more the properties of alkanes. But before we do that, one more point is this idea of kinetic energy. So when we heat a substance, when we heat particles, they gain kinetic energy. They start to move faster, basically. So if you heat the particles in a liquid or in a gas or in a solid, they start to move more quickly. And this basically relates back to just particle theory stuff you would have done in your junior years at high school. And the more kinetic energy the molecules have, the more likely they'll have enough energy to overcome that force of attraction between molecules, those intermolecular bonds. And if they can break those, they'll come apart and potentially even turn into a gas. So if we look at that, this is what starting with solid, this is what a solid looks like. We've got particles here, so each of these balls represents a molecule. It could be a single atom, but let's pretend for a moment that each of these balls represents a molecule, and the molecules are attracted to each other. And as we heat them up, the molecules will all start to vibrate more quickly. But the force of attraction, the intermolecular bond or force, is strong enough to hold the molecules in a regular pattern. So the force of attraction between this molecule and its neighbouring molecules is strong enough to hold them in a fixed pattern, and that's a solid. But if we continue to heat it, eventually these molecules gain enough kinetic energy that they can overcome the intermolecular bond, that force of attraction between molecules, that they won't completely escape each other, but in the liquid phase they can all sort of slide past each other. So the force of attraction between the molecules is now strong enough that not quite strong enough that they can escape each other entirely, but strong enough that they don't that they can escape that fixed pattern and all slide over each other. And that's when we get a liquid. And this actually explains why liquids can be poured. The molecules within the liquid can all slide past each other. So if this was water, liquid water, each of these balls represents an H2O molecule, and there's enough energy, the temperature is high enough that they're still sticking together. The force of attraction, the intermolecular bonds are strong enough to keep them stuck together, but they can slide past each other and slide around and as kind of a sticky mass. However, each of those is still an H2O. The hydrogens and oxygens aren't actually splitting apart. We haven't nearly got enough energy for that. So if we keep heating it even further, we get to the gas stage. So now we've provided enough energy to completely overcome those intermolecular forces or bonds, and the molecules can now completely escape each other. So we've provided enough heat energy, which is basically, if you didn't know that, if you measure the temperature of a substance, you're just measuring how fast the particles are actually moving, how much kinetic energy they have. So when you heat something up, you're just giving the particles more kinetic energy, they're moving faster. So we've heated this sufficiently now, so maybe we've gone past 100 degrees. If this is water, it's boiled, it's turned into a gas, and so we now have H2O molecules that have overcome the force of attraction, the intermolecular bonds, and they can completely escape each other, and they all fly around separately like this as a gas. If we continue to heat it even further, eventually we might be able to provide enough energy to actually break the bond between the hydrogen and oxygen atoms, to actually break the bonds within a molecule. But those covalent bonds, so again, if I draw, so this time I've been using H2O as an example. So if I've got my hydrogen and my oxygen, and let's draw another one over here. So the force of attraction between each molecule, the intermolecular bond, so the force of attraction between each molecule is weaker, a lot weaker than the force of attraction or the bonds within a molecule. So what we're saying is that intermolecular bonds are weaker than the intramolecular bonds. And what that means is when we heat these substances up, the molecules will separate, start to slide past each other, liquid, then escape each other completely, turn into a gas, usually before we actually get the atoms breaking apart and a chemical reaction occurring. So in most cases, we could say that the intermolecular bonds are weaker than the intramolecular bonds. These covalent bonds are really, really quite strong. So what does that mean? How does that relate to the property of alkanes? Well, let's have a look at the property of alkanes. So the melting point is the temperature at which a substance changes from solid to liquid, and the boiling point is the temperature at which a substance changes from a liquid to a gas. And if we look at, say for instance, the boiling point of alkanes against, so this is the temperature at which they boil and the number of carbon atoms, you can see the longer they are, the higher the boiling point. So the longer the chain of carbon atoms, the higher the temperature is going to need to be to turn it into a gas. So for instance, if it's only one carbon atom, methane, so that's methane at room temperature, that's a gas. And we know methane is a flammable gas. Ethane is also a gas, propane is a gas, butane is only just a gas. It's not far off. In fact, if you put butane in your freezer, I think at -4 or 5, it will turn to a liquid. But once you get to sort of 5 and 6 carbons long, then these alkanes will be liquid at room temperature. You actually have to heat them to a temperature higher than room temperature to get them to boil or to turn into a gas. So the boiling point increases the longer the carbon atoms get. And the same is true for the melting point. Now all of these are gas or liquid, but if we go further up, for instance, alkanes say that a 30, 40, 50 carbons long may even be solid at room temperature. So the boiling and melting points increase. You need higher temperatures to get them to boil or melt as the molecules get longer. So why is that? Well, basically, so we said here, the boiling melting points of straight chain alkanes increase with their length. So as they get longer, their boiling or melting points get higher. And the reason for that is they have greater intermolecular forces acting between each molecule. And what do I mean by that? Well, if we take methane as an example, so if I've got methane here, just CH4, sorry, a little bit messy. There's a force of attraction in between them occurring here. But if I take something like propane, and maybe this time I won't bother, or let's say even butane, 4 carbons long, I won't bother drawing in all the hydrogens, it'll just make you wait. But you can see if I've got a 4 carbon chain, and you can imagine all the hydrogens around there, we've got a force of attraction between the molecules occurring here. It's a much larger area over which you've got that attractive force. So essentially, you're going to have a stronger force of attraction between longer chain molecules. So as they get longer, the intermolecular force in between here, in between the molecules, becomes greater. Now you'll notice I sort of qualified this, I put straight chain alkanes. Well, if they're really branched, then it can be kind of more difficult for them to compact or to lie next to each other. So that can actually weaken the intermolecular forces. But as a general rule, or this works, if we're talking about at least straight chains, and in general, the longer and bigger they get, the larger the intermolecular force between them. So basically, the stronger the force holding them together, the more energy, the more heat, or the higher the temperature you're going to need in order to break or overcome that force of attraction to make it melt or even evaporate, to turn it into a gas. So when we're melting or boiling, what we're doing is we're starting to break some of, or when it boils all of, these intermolecular bonds, the ones holding the molecules together. And so the larger the molecule, the stronger the intermolecular bond. It's that simple. So that's one of the key properties of alkanes, that the longer the chains get, the higher the melting and boiling points, because the stronger the intermolecular bond between them. What causes this intermolecular bond? Well, that's getting into sort of really advanced stuff, but just to give you an idea, the electrons in these molecules aren't stuck in one position. They're sort of flying around, and you've got on average kind of 2 being shared in between, but there is some movement of those electrons. And what that means is that at any given time, there might be a few more on one side than the other, and so you get slightly positive and negative areas, and you can get a corresponding positive-negative match in the other molecule. And so that instantaneous kind of at certain times uneven distribution of electrons makes weak positive and negative areas that are sort of attracted to each other. Like I said, you don't really need to worry too much about that. You'll learn more about that at kind of the senior levels as you progress. But the key idea here is that as the molecules get longer, the intermolecular forces between them get stronger. Cool. Okay, so trends. Just a just to finish there, as alkanes increase in length, they have higher melting and boiling points. They're also more viscous. So if we're talking about liquid alkanes, the longer chain liquids versus the shorter chain liquids are more viscous, and that kind of means a more thick liquid. And that makes sense because, again, the intermolecular bond, the force of attraction between the molecules, is stronger, so it requires more energy to make them slide past each other. It's going to be a slightly more viscous fluid if it's a longer chain molecule. Another trend that's often listed in some textbooks is the longer chain ones tend to burn less cleanly. They tend to burn sort of more smoky or produce soot. And as you may know, or may have covered, or may learn later, that's an example of incomplete combustion. So the shorter chain ones tend to burn are more likely to burn by complete combustion. So they tend to burn more cleanly. The fourth one here, I've seen in some textbooks a reference to colour, that as they get longer, some of them get darker in colour or become coloured. I'm not so completely convinced with that. I mean, candle wax, for instance, is an example of very long chain alkanes, and it tends to be white, unless it's artificially coloured, unless colour is added. But your short chain ones are definitely colourless, don't have colour. So colour, I've put it there with a question mark. Some of your longer chain ones may be coloured, but I'm still a bit dubious about that one. The real key ones here, though, is the higher melting and boiling points. They do become more viscous, and they tend to burn less cleanly as they get longer. So I hope you found that helpful. That's the properties of alkanes. And actually, these properties, you tend to see similar trends for some of the other hydrocarbons or organic molecules too. So as a general rule, if molecules are longer or larger, there'll be stronger intermolecular bonds or forces of attraction between them. So that's it for the properties of alkanes, and we'll get on with the next one.